Good day, everyone. This is Module 8, Dynamics of Rotational Motion and Equilibrium of Rigid Bodies. In this figure, or in this slide, you have two figures. Ang isa ka person, this one, pulling a crate, and a seesaw here. Now, if we convert this one into a free body diagram or FBD, it would look something like this. So the person pulls the crate with a force F. So that's why ang direction niya padulong diri. And ang crate pod kay naa siya'y weight W. So naa siya'y weight here. O ang surface interacting with the crate naa siya'y normal force, which is perpendicular to the surface. So it's always 90 degrees. So as you can see, kanilang ang forces na diri. Also, manotice nimo, wala kay friction present. If na friction normally, naa siya diri, going against the direction or sa pull sa imuhang force F. The other figure is ang kaning seesaw. So ang seesaw, if na siya, let's say, in equilibrium or balance siya, it would look something like this. Ang iyahang sort of equivalent sa free body diagram. So naa kay point of rotation or tawag na fulcrum, okay? And this tells you that the direction is going clockwise, indicated by this curve circular arrow. Pag naa siya'y force, apparently ang force niya mas bugat diri kay na napaana man siya mas mopabor man siya on one side. In this case on the right side. So this force F, if balance siya, it would be 90 degrees with respect sa kaning beam. And this distance, or sometimes called as the torque arm, this distance is the measure from the fulcrum, the point kung asa siya mo rotate o asa nag-interact ang imuhang force. Now this force plus kaning distance gives you the physical quantity called torque. Now what is torque? Torque is defined as the quantitative measure of the tendency of a force to cause or change the rotational motion of a body. It is denoted by the Greek symbol tau. So in general, ang torque or ang tau is a function of r. This is the distance from the point, the pivot point or the fulcrum point towards the asa nag-interact ang imuhang force F. And it is a cross product. So before going further, let's look at unsa ang cross product. So let's recall. So if you have two vectors, A and B, and these A and B vectors lie on the same plane, to find the cross product, we simply use this right-hand rule. So as you can see, ang base sa palm sa imong right hand goes against the direction sa imuhang second vector B. Then it curls, tuyok siya padulong sa imong vector A. The direction of the thumb indicates the direction of vector C. Now, you have here a figure of a screw. So sa screw, same gyapon. Ang base ani niya is lying on the same plane sa imuhang two vectors, A and B. Then, ang imong right hand would curl sa direction sa imuhang screw. And the tip is just like the thumb, indicates the direction of the vector C, which is the cross product of these vectors A and B that lies on the same plane. So as you can see, ang vector C is perpendicular to vectors B and vectors A. Perpendicular siya sa plane. Now, the magnitude of C is given as a function of the magnitude of A times B times sine phi. Phi is, of course, the angle between the vectors A and B. Okay? So if you're asked to determine the magnitude, we simply multiply AB sine phi. This is different sa imuhang scalar product. Okay? The scalar product nimo is a cosine function. Here is a sine function. So, the torque now, ang magnitude sa torque is just the radius times the force times sine theta. Theta is just the angle between the vector of the radius or the distance from the force to the point of rotation or vice versa and the force F. And it can be simplified ang kaning R times sine theta as L. L is the moment arm. Moment arm ni mo ha. Okay? So the torque function, again, just like this one, the base of the palm goes against the direction of the force, curls towards the direction of the radius the distance r, and the tip of your thumb indicates the direction of the torque tau. Now, if we have this example, you have the point of rotation, the point of interaction sa imong force. So first, we replicate this in a free body diagram. So nakay force F. So sa force F ni mo ha, ang imong base imong palm will go against the direction sa imong force, then it curls towards the direction sa imong r or ang distance, and the blue dot indicates the direction of the torque, okay, in this dot. Okay. Ang opposite ana niya, if it goes into the page, is an X nga mark. But since this one is going out of the page, pagawa sa kaning plane, kaning slide diri, it's a dot na symbol. Bulihan na natong blue nga dot. Okay, I hope that's clear. Then let's proceed. So here we have to look a scenario. The first scenario is that nakay vector A, not vector A, nakay condition A, then B and C. Sa A, you have the force causing the body to rotate counterclockwise, as indicated by this direction. Sa B, it will cause the body to rotate clockwise. So let's first examine kaning 2. So what we do is we convert na to FBD. So this point of interaction will be the origin, and you have the force F and the distance or the radius r. So again, the base of your right hand goes against the direction of F, then it curls towards the length r. Therefore, so using right hand, the thumb indicates that it is going out of the page, pagawas, padulong sa imuha. So the magnitude of the torque is just Rf sine theta. Sine theta is of course equal to 1. And since it's going outward, we indicate here a positive nga sign. Okay, kung graphical, it's a blue dot or it's a dot. You don't have blue na pen. The second condition, ang sa B, is you have the force F on the other side, and this will cause the body to rotate clockwise. Again, the point here will become the origin, and we transfer the force and the radius here. So as you can see, again, the palm goes against the direction and goes against the direction of F, and it curls towards the radius. So kung imong hand imong gamiton, awkward siya kay pasulod siya sa page. So that's why na kay X mark. Again, the magnitude of the torque is just the same. It's Rf sine 90 degrees, and this gives you 1. This is just Rf, or for this case, FL lang siya. Okay, R times sine 90 degrees is L. Now, we indicate here it's negative. Okay, inward man siya. It's indicated as inward. The last condition is that you have the force directly onto the pivot point. Oh, pivot point siya. So, the angle between them is either 0 degrees or 180 degrees, either padulong or pagawas. So, as you can see, sine 90 degrees gives you 1, but sine 0 gives you 0. And of course, ang the distance between F and R is also 0. So, 0 siya. So, the forces na directly lying or intersecting, kung asa siya mo rotate, will not cause the body to rotate clockwise or counterclockwise. Now, let's look at the same thing, but this time it's for a rigid body. So, you have tulog gihapon ka scenario. Let's look at scenario A. So, you have here the force F intersecting on a certain point here. Again, we use this one as the origin point. Convert that one here. So L is this one, the length, or for this case, it's called the moment lever arm, which is again L sine theta. And you have the F. Now theta here is of course, they're just perpendicular with each other, so 90 degrees. So just like ang kaganina na scenario, you have the palm, the base of the palm goes against the direction of F, and it curls towards the moment lever arm. So therefore, that siya indicating that the torque is going out of the page or padulong sa inyuha. And mathematically, ang equation of the magnitude is Rf sine 90 degrees. And of course, this gives you 1. And R sine 90 degrees is just L. So it's just positive FL. Again, same reason, positive siya ang ibutang because it's going out of the page. The next one is this one. Also, you notice na gitawag diri nga line of action. It's just a direction kung asa ang imong force. So for this case, this will rotate the body clockwise. Yeah, clockwise. So the line of action is going here with sabay siya sa direction sa imuhang force F. And we denote this point here as the origin. So na kay L dira, just like this. Then you have the force F. Again, using the base of the palm goes against the direction. It curls towards L, thus na kay X, indicating that the torque is going inward or into the page. So we put a negative sign here. Same function gyapon class kay 90 degrees naman gyapon ang angle between the moment lever arm and the force F. The last one is just the same gyapon. Ang line of action directly hits the point of rotation. So the angle between them is 0 or 180 degrees. And as you know, ang sine 0 is 0 o ang sine 180 is also 0. The distance r or L is also 0. So doesn't really matter. So no rotation. So pag mo intersect siya sa imong axis of rotation, force nimo ha. So wala siya contribution sa rotation. Okay, I hope that's clear. Let's go. Next, we have the torque and angular acceleration for a rigid body. At this time, it's in a three-dimensional axis, okay, X, Y, and Z. So this one is X, Y, and Z. And this one is rotating sa axis nga Y. Rotating sa axis nga Y, it is, And considering ang isa ka particle, because you have so many particles, we consider that singular na particle and consider ang direction sa rotation is just this way. Siya, so kung lantaw mo sa top view ni mo sa y-axis, so it's rotating counterclockwise with respect sa y-axis. So this one, ang kaninga particle, na siya at a distance r1 with respect sa imong y-axis. And as you can see, na kay mga forces dira. So if this is rotating here, this one is the force tangential experienced by that mass. Of course, napod kay F1y, which is moving upward, perpendicular sa R1. And you have the F1 radial going out sa imuhang, siya. Align siya sa imuhang distance R1, but it's going outward. So, as you can see clearly, ang F1 tangential lang ang nag-contribute here sa motion sa imuhang particle around the axis nga y. So tangential component is F1 tangential, so relates to the mass 1 tangential, then acceleration 1 tangential. But if you remember, ang acceleration tangential in relation to angular acceleration is given as R1 alpha. Okay, so F1 tangential, substituting this value or this equation back to our F1 tangential is M1 R1 alpha. Now, we multiply both sides by R1. So this becomes R1 F1 tangential and this one M1 R1 squared alpha. Why is that? Ano gi-multiply man na to? Then you can see sa next slide. So R1 F1 tangential, we know this to be the torque. The torque wherein the angle between R1 and F1 is 90 degrees. And as you can see, indeed, 90 degrees ang ilang relationship. So this holds. And M1 R1 squared, from the previous topic, this one refers to the moment of inertia. So we can write an expression for this mass in terms of torque niya is equal to I1, or torque 1 for that mass 1 is equal to I1 alpha. Okay, and again, both the F1y perpendicular and F1 radial does not contribute to the torque because ang ilang direction does not cause the body to rotate in a manner that is counterclockwise with respect to the y-axis. Next, so if this is for the torque 1 for the singular mass, if you consider all the masses, so R1, the torque would be the sum of torque 1, torque 2, torque 3, so and so, which is equal to I1 alpha, I2 alpha, I3 alpha, so and so. So the angular acceleration remains constant, but the torque and the moment of inertia changes. So if you sum the torque to get the torque net, it's just equal to the sum of MIRI squared, where I is equal to 1 to n particles. So, and that refers to the I total as I alpha. So the torque net can be expressed as the moment of inertia times the angular acceleration. This means that the sum of the torques acting on the body is proportional to the angular acceleration alpha. Okay, so this equation is the rotational analog of Newton's second law, which we remember is the force is equal to mass times acceleration. So it's just analog niya. Of course, this galing lang sila parehong units kay. Remember, the torque is force times a distance. Okay, let's go. So the condition for equilibrium can be changed. So the first condition so far that we learned is that the sum of the forces must be zero, meaning the sum of x, forces along x is zero, the sum of forces along y is zero, and the sum of fz, zero for 3 dimension. Here we add a second condition that the sum of net torque must be equal to zero. Okay, posible man siya na if you have this object here, you have force F and force F here. Obviously, if the force F is equal to this one, the sum of force along X is F minus F equal to zero, but this will cause the body to rotate. So, para di po siya nag-rotate, we need to sum the net torque equal to zero. Okay, so these are the two conditions. Hopefully na kuha ninyo, ha? Let's go. So we have an example here. A sign of mass 20 kilogram hangs from the end of a rod of length 2 meters and a mass of 4 kilogram. Okay? A wire attached to the end of the rod to a point of 1 meter above the origin. Letter A, find the tension on the wire, and B, find the force exerted by the wall. So it's just exerted by the wall would refer to the force along X lang. First, we draw an F. So this one refers to the rod, weight sa rod, and you have the mass, weight 2. You have the wire, the tension sa wire, force na siya tension along X and tension along Y. And you have the force Fx and Fy. So iyahang net would be this. Okay, let's go. Next is we apply the rotational motion for equilibrium, or the second condition to solve for the tension T. This one. So we sum the net torque should be equal to 0. So the net torque can be divided into 2. The torques na contribute sa clockwise direction minus the torque that will cause the body to rotate counterclockwise. And this one is 0. Okay, so let's see. So the torque na mag-contribute sa clockwise, if we assume na kanisya ang pivot point, clockwise would refer to, let's identify first the forces. So you have the force F, then you have the weight 1 and weight 2 and the tension. So first is force F. The force F would not contribute to any rotation kaya it's directly lying sa pivot point. So that's why 0 siya. The next is weight 1. If this one is allowed to move freely, this force will cause the body to rotate clockwise. Yeah. This one also, if it's allowed to move freely, let's say wala connection ng tension 1, this one will cause the body to rotate clockwise also. The tension will cause the body to rotate counterclockwise. Okay? So, isa lang ang nag-cause of counterclockwise. And we put here a negative. Let me clear this a bit. Okay, so na-establish na nato mga forces of unsay lang effects in terms of rotation, clockwise ba o counterclockwise. So, let's look at weight 1. So, weight 1, na siya distance from the point of rotation as R1. So, R1, weight 1, sine 90 degrees because 90 degrees man ang angle between R1 and weight 1. R2, weight 2 is the same. Ang angle between the distance from the point of rotation o sa point of interaction sa imong force is also 90 degrees. So this one is 1, this one is 1. Ang R2, tension 2, dili siya 90 degrees. It's some angle theta. So we keep this, we preserve this. So we know weight 1 as M1G, okay, and this one as M2G. So that means we can factor out ang mga G, R1, M1 plus R2, M2. And kanisya, we simply transpose it to one side and we bring down this one by crossing. So muna na siya sa ubos. So the tension, the expression for the tension is G R1 M1 plus R2 M2 over R2 sine theta. However, we don't know pila ang, or not pila, but unsang expression sa theta. So theta can be done easily because we already know na ang beam ni mo ha 2 meters o connected ang wire sa wall by 1 meter with respect to niya. So we can use the tangent function. Tangent function is equal to the opposite 1 meter over 2 meters. So theta is the tangent inverse of 0.5, or it is 26.6 degrees. Okay, and we can substitute this one here, and we get the value of sine of that one as 0.447. Now, substituting ang G na 9.8, ang R1 na 1 meter, ang M1 na 4 kilograms, then ang imuhang R2 na 2 meters, then ang mass na gi-attach sa end sa imuhang sa beam is 20 kilograms, and you would get something like this. Divided by this one, and you arrive to the tension of 483 newtons, 483.6 newtons, around that number. Next, applying the condition for equilibrium, or the first condition to solve for the force X. The force X is just the force na gi-exert sa wall. So wala na to gi-solve ang Fy, pero since nata dire, i-solve na lang nato. Pati pod ang pila ning Fv. So to solve that one, we sum the forces along X and along Y. Along X, you have Fx going in the positive direction. Okay, this is the x-axis. Minus, isa rami nag-minus na niya, which is ang Tx. And Tx can be expressed as T cosine theta. And we know theta to be 26.6 degrees and T as 483.6 newtons. So you multiply those two together, but don't forget to cosine it first, and you get the force exerted by the wall is 432.4 newtons. Since natin dire, let's solve na lang po ang Fy. So you have, along the sum forces along Y, you have Fy going upward, then plus Ty going upward, minus weight 1 and weight 2. So weight 1 and weight 2 is just M1G, M2G. So we factor out the G here. And before that, ato sa ning i-transpose ni silang duha sa pikas nga side. So hence, ma-positive na siya. Okay? Kung ang Ty ni mo, transpose mo sa pikas, becomes negative. So Ty is just T sine theta. T sine theta. And then Fy, substituting the values, is equal to 9.8 meter per second squared times 4 kilograms plus 20 kilograms minus 483.6 newtons sine 26.6 degrees, and you have a value of the force along Y, kanisha 18.7 newtons. Okay, so let's try to solve pila ang value sa F, and we use Pythagorean theorem. So from the previous slides, we get 432.4 newtons sa Fx, Fy 18.7 newtons. You square both and sum them, and you take the square root, you get 432.8 newtons getting a force. Okay, that's clear. Let's proceed. Oh, we have another problem. You have a ladder whose length is 12 meters and whose mass is 45 kilograms rest against a wall. Its upper end is at a distance of h of 9.3 meters above the ground, as in figure 8-10. The center of gravity of the ladder is 1/3. Okay, somewhere here. If it is divided into 3, 1/3 siya. Way up the ladder, a firefighter whose mass is 72 kilograms climbs halfway. So na siya sa L/2. Ano siya? Assume that the wall but not the ground is frictionless. Okay? Smooth ang wall. Pero kani siya rough siya friction. What force are exerted on the ladder by the wall and by the ground? Okay, let's go. So this is a free body diagram. Okay, this is a free body diagram of the system. You have the ladder here, and you have the height, which is 9.3 meters, given as siya. The ladder L is also given, and you have the masses. So therefore, kung may masses, you know the weight of the person, weight of the ladder. And forces present is force exerted by the wall. Of course, kay padana siya, pili siya sa wall. So the wall will exert a countering force. Then you have of course, the weights, and you all have the friction on the ground. If it is stationary, this is Fs. So, then you have the normal force by the ground, of course. Let's go. So we use the second condition for equilibrium. Okay, so we will consider this point here as the point of rotation. Okay, kanisha smooth man so probably mo slide na siya. Let's say kanisha is na friction siya nagapugong, so there probably ang rotation iha. Again, we sum clockwise or counterclockwise using kaning forces na available. So first is this one, force by the wall. So if it's allowed to move freely, this force will cause the body to rotate clockwise. Okay. Weight by the person, of course, this one will cause the body to rotate counter, so negative. This one, weight sa wall, will cause the body to rotate panaugpod. Now, ang imong force Fs, let's say stationary, force by the static force, static friction, o ang normal, they are interacting at the point of origin. And this one will not contribute to anything. Not contribute to anything. So, ang nabili na lang, sa nabili na lang. And nabili na lang kaning tulo by the force of the wall, by the weight of the person, and the weight of the wall. So if we transpose these two equations on one side, it becomes positive. So torque, remember, is R cross F, force by the wall. So R cross F. So if this is R, so that would be the length, the total length of the ladder, ang magnitude L, force by the wall, sine theta. It's the angle between the force of the wall o ang length sa ladder. Okay? Next is ang imuhang weight by the person. Let me clear this. Next is weight of the person. This one obviously is equal to the length is, ang weight sa person is halfway man. So that's L over 2 ang yang R. Ang force niya is ang weight by the person sine phi, the angle between the ladder and the force, weight P. Okay? Next is ang imuhang weight sa ladder. Weight sa ladder, ang iyahang location, ang iyang center of mass is located 1/3. 1/3 sa ladder. So that's L over 3. Sine phi again. So if we rewrite, ang force sa wall is G sine phi over sine theta is equal times mass of the person over 2 plus mass of the ladder over 3. So we need to solve the angles, ang imong phi o ang theta. Wala man takabalo. But that's quite easily done because we already know na ang iyahang length or ang iyang height is h, ang iyang length is longest distance, ang iyang hypotenuse is L, ang iyang base is A. Okay? So sine phi na function is equal to h over L. Ang sine theta din. Ang sine phi nimo is, ang opposite niya is A over L. So we don't know unsa ning A, but we know this is a right triangle. We can use the Pythagorean. So L squared is equal to A squared times plus H squared. Okay? So A squared, transpose nimo ang H on one side. So this becomes minus H squared. So A squared is equal to L squared minus H squared. Taking the square root of both sides, you get the function for A. So sine phi becomes ang A nimo is equal to L squared, square root of L squared minus H squared over L. For L na siya. So, solving the ratio of the sine functions, so you have sine phi is equal to square root of L squared minus H squared over L divided by sine theta. So H of L, this becomes L over H. So sine phi over sine theta is this. And we can substitute this one to our equation. Okay, substituting this one here gives you this function here. And we then substitute the values mga given. Ang L, ang imong H, ang imong MP, ang imong ML, and of course, ang G nimo, which is 9.8. So substituting that one, doing the necessary calculation, gives you the force of the wall, exerted by the wall onto the ladder, which is 407.5 newtons. Okay. So next is we figure out ang objects moving with translational and rotational motion. Just like this one, nag-rotate siya, then nag-move po siya along the axis. So naa kay translational, which is the velocity of the center of mass, ug naa kay rotational motion, which is given by the angular velocity. So this rigid body moves in both translational and rotational. Okay, nice. Let's go. By the way, so far atong gipang consider sa kanang translational motion, like kanang mga cars, ang ligid wala nagatuyok, naga-slide lang siya bali. But this time we're gonna try to correct that one. Okay. So let's look at the free body diagram. This one is in 3 dimension. Nag-rotate siya. It's rotating on about the y axis, counterclockwise. So again, we use the mass particle M1. This mass particle M1 naa siya mga velocities. Na kay tangential velocity ang kaniyang V prime I, then na kay velocity sa center of mass ang nagamove translationally, ug na kay VI, which is, ang VI is the sum of the duha ka velocities, ang tangential ug ang translational, ang VCM. So VI, kani siya. So na kay VCM ug VI. So VI is like this. So since energy atong ginahisgutan ani and this particle is moving, so we need to solve for the kinetic energy, which is 1/2 mi VI squared, which is equal to 1/2 mi. And we know VI is given by the sum of VCM plus B prime, which is the tangential. Yeah, tangential. You multiply the two, you get VCM squared. Take note, this is a dot product. And kinetic energy is a scalar quantity, so dot product siya. Then you have 2 VCM dot VI prime, V dot V prime. Okay, so this becomes V prime squared. Let's go. So the total kinetic energy for the whole body, K total, is the sum of the KI's, 1/2 mi VCM plus mi VCM dot V prime plus 1/2 mi V squared. Okay, take note that product ni siya, so cosine siya na function. So the angle between ang imong VCM and VI prime, the tangential o translation, is 90 degrees. If we go back to the figure, see, VCM here, VI prime here, so this is 90 degrees. So cosine of 90 degrees would yield to 0. So mawala ning middle nga term. This becomes 0. So you have the kinetic energy total is the sum of the VCM, the translational part, and 1/2 mi VI squared. Okay, 1/2 VI squared. And this one can be rewritten as the sum written as the moment of inertia of the center mass times the angular velocity squared. So na kay translational o na kay rotational component sa total kinetic energy of a body when it is moving translationally ng straight na mga path, or plus ang ihang rotation na kinetic energy. Okay, nice, right? So we can analyze the combined translational and rotational motion of a rigid body. This is for the translational, and this is the analog niya sa imong rotational, which is the sum of the net torque, which is equal to the moment of inertia of the center of mass times angular acceleration. Like this problem here. So na kay translational, pasaka, kanipon siya, panahog here, and na kay rotational here. Rotational. So the second equation is valid even if the axis of rotation moves, but it must satisfy the two conditions. The axis of the center of mass must be an axis of symmetry. Letter B, the axis must not change direction. Okay, let's go. From this figure, the disk pulley, kanisha, has a radius R. And a mass M. So, mass M na kay disk pulley. You can go back to the table to obtain the expression for the moment of inertia of this mass. The surface between M2 and the ramp is frictionless. So wala friction. It's not frictionless. Mantura na siya mu k dira. And mu k, so it is the friction related to motion, so na kay movement, of course. Otherwise, wala na nagbublitan. If the mass M2 slides downward to the left, while the mass M1 moves upward, derive an expression for the acceleration of the masses. Find the tension T1 and T2. So, first we draw the FBD. So, tulo ka ba itong atong i-consider? Mass 1, kaning mass 1, nagasaka ka naog lang siya. So, tension lang. Og ang force na siya, mass na siya, weight 1. Wala siya x-axis, only y-axis lang. For mass 2, it's on a ramp. So, kay x and y-axis. Again, we consider the surface of the ramp as the x-axis. So, panaog man siya, paano siya dira. Ang imuhang normal force is perpendicular to that one. Ang imong weight is directed towards the center of the earth. So, na siya components, weight 2x o weight 2y. And nakay friction. O nakay tension pa dyan. Okay? Next is ang pulley. Ang pulley ni mo, duha lang ka forces ang nadira. Ang tensions, T1 and T2. So you have the mass M, so nakay moment of inertia. Of course, nakay angular acceleration, kaya nag-rotate man siya without slipping. So naka moment of inertia here. Okay, this is a disk. Okay, let's go. So for mass 1, you have the sum of forces along y. Since it's moving, this is 0, so it's m1a. So the m1a is contributed is due to the difference of the tension minus weight 1, which is called m1a. Tension can be written as this, and weight 1 can be written as m1g. So tension 1 is equal to m1g plus m1a. So again, di pa natin. This is the unknown here. So fx is just 0 kaya wala may motion along the x-axis. Next is ang imong mass 2. So again, okay, weight 2, tension 2, normal, and the friction related to kinetic. So we divide them into two, the fx and the fy. So fx na kay negative tension 2 going in here, the negative friction, kinetic friction going here also. Then you have ang counter saya is ang weight 2x going here and equal to m2a. Tension 2 can be written as weight 2x by transposing this side o kani siya i-transfer po nimo diri. So weight 2x minus fk minus m2a. Weight 2 is weight 2 sine theta, fk is mu k times the normal minus m2a. And this weight 2 is m2g sine theta mu k, and the normal is obtained from the force along y. Sum of force along y. The sum of force along y, let's solve first this one, is equal to 0, wala may motion along y. So na kay normal pasaka minus weight 2y panaog. So the normal, transpose nimo na dira, is weight 2 cosine theta, which is m2g, which we substitute here. Then we add ang negative m2a. So this is now the expression for tension 2. Again, we still don't know, okay, unknown man siya. But we have enough equations na, okay, equations to know. We also did ang third, how to combine tension 1 and tension 2. So we use another condition, but which is the sum of torque is equal to ICMA. ICM times angular acceleration. So you have torque 1 and torque 2. So torque 1 related to this one will cause the body to rotate counterclockwise. And the distance r nimo is 90 degrees. So it's that one. Okay, cross product. Next is ang tension 2 or sa torque 2 nimo. Again, this one is due to T2 times r sine 90 degrees. Okay, 90 degrees man ilang relationship. This is 1 and this is 1. Okay, and this is negative. Is equal to 1/2 mr. 1/2 mr, which is the moment of inertia for this disk. Okay, times a. And we can cancel out ang r's niya. And unsa pa? So tension 1 minus tension 2 is equal to 1/2 ma. Okay, 1/2 ma. This is equation D. Oh yeah, by the way, ang alpha, ang angular acceleration na to is written this way. So alpha is equal to A tangential over r. And since A tangential simply refers to the acceleration over r. So that's why napulihan siya o kani. Okay. Yeah. That's why here, isa na lang ka r na bilin kani cancel out. Okay, I hope na follow na ninyo. So what do? Now we substitute. Substitute na. So we have the equations A sa tension 1, equation B, and equation D. Substituting them, ang kaning T1 here o ang T2 here. So you have M1G plus M1A, M2G sine theta minus mu K, M2G cosine theta minus M2A, 1/2 MA. Then we can group ang like terms. This one, transpose nato here. And this one, transpose nato. Sorry, this one transpose nato here. And this one, transpose nato. And we factor out the A. So you have M. And this one, mag-cancel. 1/2. So it gives you this equation here. And this one, factor out nato ang G. So ang acceleration A is equal to this equation here. Call this one as equation E. Okay. Double check na lang ninyo class. Ito ba ni? Pero you get the flow. Then, to solve for tension 1, we use the solved equation A and substitute it to equation A. So tension 1 is equal to M1G plus M1A. Substitute here and you get this long equation. Okay, this is tension 1. Similarly, for tension 2, we use the same equation A, substitute it here, and you should arrive something like, so medyo kuti siya. Not really kuti, like haba lang siya. You have to be careful lang sa mga variables na unsan mga variables na. Okay? Next, we talk about work and power in rotational motion. In rotational motion, we can express work in terms of the torque and angular displacement. Angular displacement, d theta. So if we have an object here, nagamove siya from this point to this point, nagamove siya by some arc s. If you try to create something something really small, small na siya na arc, it's ds. And that would move in a small angle na d theta. But still, F tangential gyapon siya. So we recall that this work is just, ang work nato expression is F times D. So that means dW is F tangential times ds for a small amount of work. So ds is the arc length, and ds, we remember, is just r times the small change in theta. So that means dW, the small work, is equal to F tangential times r d theta, which is the ds. So dW is equal to torque times d theta, because this F tangential times r gives you the torque expression. Of course, this should be 90 degrees in relationship. 90 degrees in relationship. Now, dW, which is now torque times d theta, we can sum this by integrating. So, ang torque ni mo kay constant naman siya throughout. So, d theta lang ang nag-change. So, work is equal to torque d theta, and theta measured from theta 1 to theta 2. So, this becomes theta 2 minus theta 1 is equal to change in theta, ang work ni mo. So, angular, as I said, it's an angular displacement na function sa work ni mo. Okay, let's go. Also, this small amount of work can be expressed in terms of the moment of inertia, because the torque, remember, nasolve nato ni, is equal to the moment of inertia times the angular acceleration. So substituting this one to here, so I alpha, I is equal to alpha d theta, and alpha, if you remember, is just d change in angular velocity over change in time. Okay, and so you have this one here as a replacement of here, and we can swap na to initial diri, and this gives you d theta over dt, which is d theta over dt as omega, or the angular velocity, times dw. Then to solve for that one, we integrate here. So this becomes omega squared, integrate ni mo na siya, this becomes I omega squared over 2. So hence, mo na siyang 1/2 I omega squared. So if you integrate this one from omega 1 to omega 2, you get this expression, work expression, as the change in moment of inertia. Okay, change in moment of inertia and angular velocity. So the work equations you have here is equal to this one can be factored out. This one can be factored out, and this simply becomes the change in omega squared. So omega, the work is equal to torque times change in angular position. Next is, of course, ang work ni mo, ha. Next is ang power. Power, if you remember, is the change of work over change in time. So if we know this, that work is just this one, torque change theta, change in angular position over change in t. And this one is angular velocity. So power is just the torque times the angular velocity. So that's it. Let's look at some example. You have a flywheel of an engine has a moment of inertia of 2.5 kilogram meter per second squared about its rotation axis. What constant torque is required to bring it up to an angular speed of 400 rev per minute in 8 seconds starting from rest? And letter B, what is its final kinetic energy? So the given is that nakay angular velocity na 400 revs per minute. Starting point is at rest, so the angular velocity is 0 rev per minute. Ang time niya initially at 0, and ang time niya later is 8 seconds to achieve the angular velocity na 400 rev per minute with a moment of inertia of 2.5 kilogram meter squared. Okay, let's go. So the constant torque required can be solved using this expression here, I alpha, and alpha is just the change in the angular velocity over change in time. So the torque is I, substitute here on delta omega over delta t. For that, let's first convert ang imong angular velocity. So from rev per minute, we convert that one to 40 radians per second. So we multiply 1 rev is equal to 2 pi radians. 1 minute is 60 seconds. So the angular velocity after time t is equal to 8 seconds is 40 pi over 3 radians per second. So substituting that one here. So ang moment of inertia given naman 2.5 kilogram meter squared over the time t, which is 8 seconds. And this gives you the constant torque around 13.1 Newton meter for this scenario. Okay, let's go. Next is, what is its final kinetic energy? So work in terms of, or the kinetic energy is given by the expression of the change in omega, or this one is 1/2 I delta omega, or delta omega squared. So the kinetic energy is 1/2 I omega squared minus 1/2 I omega squared. Since nagsugod siya at rest, so this is 0. So this second term here is gone. So we're left with the first term. 1/2 I is 2.5 kilogram meter squared, times the angular velocity we solved earlier, 40 pi over 3 radians per second. Let me check first. Omega. Oh, made a mistake. This should be square pa na siya. Okay, this should be, type ni siya, around 2,193.24 joules. Okay, so that should be the value here. Sorry, forgot the square. Yeah, that should be the correct answer. My apologies. Okay, let's look at the angular momentum. Recall the linear momentum, mass times velocity. In rotational motion, ang analog niya na is the angular momentum L, which is R cross P. P is the momentum. So P, we know this one as R cross mv. So L, cross product man siya. We can factor out the M one side. So it's becomes R cross V. So that is cross product man siya. So sine phi. Phi would be the angle between R and phi. R and V, sorry. R and V niya ha. I don't know why nga nung napanis siya. Wala na nang kwantera. And this one should be a scalar. Scalar? Ang magnitude lang. Yeah, magnitude. Kung magnitude lang imong kwaon. Okay. Where M is the mass of the body and L is R sine phi, the moment arm, or the lever arm. So that means ang L ni mo is just like katong sa torque is, for this case, nakay mass mi, nakay length ri, nakay vi. So again, using the right hand rule ni mo let's see, how does that look like? So nakay ri, nakay vi. So this is the angle between them. So this one would curl here and it points outward siya using right hand rule. So it's out of the page. So you have Li is equal to mi vi ri for this mass I here. So vi is omega ri, and phi is of course 90 degrees. So sine 90, wala siya. This gives you 1. So Li is equal to mi ri omega ri, because vi is omega. So mi r. So goes back to this one, and we know this one to be moment. It's just a moment. So L is equal to sum of Li's, okay, is equal to sum of mi ri squared, okay, times omega gives you this function. So in general, the angular momentum L is equal to the moment of inertia times the angular velocity. This is for a rigid body. Okay, so you have this expression. Okay, so we keep this in mind. So when a net force F acts on a particle, its velocity and moment changes, so its angular momentum may change. Taking the time derivative of L, dl over dt, you have dl over dt is dr over dt cross mv. Next is r cross m, di man siya mo change kani siyang mass, dv over dt by using the derivative rules. So v, because this one is v cross mv plus r cross dv over dt is a. So since the cross product of v cross v is 0, okay, so they have the same, because the angle between them is 0, dl over dt, yeah, because the angle between them is 0 sa v ni mo og v, and sine of 0 gives 0, so ma-eliminate ni siya na term, And we are left with this one, the second term, R cross MA. And MA, of course, is force. Okay, so DL, and of course, R cross F is just the torque. Okay, hence the rate of change of the angular momentum L is equal to the torque. Wow. Now, if the total angular momentum is L, then for a system of particles, and the sum of the external torques must be expressed as this one. Sum of torque is equal to dl over E. If the net torque is 0, then dl over dt is equal to 0. This implies that the angular momentum is constant or conserved. In scenario, if walay other forces involved ani sa isa ka body, it will continue to rotate until it is acted upon by some other external. Okay. Now, we go back a bit to center of gravity, which is just simply the location of, which can be located by simply summing the XCM, for XCM, YCM, and ZCM, summing the mass times the positions divided by the total mass, divided by total mass for X, Y, and ZCM. Okay. I actually don't know nga nung nato dito. Pero just keep in mind in 3 dimension. Okay. And that's it. I hope you learned something new today. And I'll see you next time. Bye.